This is my presentation for conservation physiology on mammalian doubly labeled water techniques. The paper is entitled Field Bioenergetics of Mammals, What Determines Field Metabolic Rates. It was published by Nagy, 1994, in the Australian Journal of Zoology. This is a somewhat older paper, but it provides a good outline of the field of biogenetics and on techniques for measuring field metabolic rate. At the end of the presentation, I will address the legacy of this paper and where it has led the field of bioenergetics today. Some background before I begin. I just want to go over the history of the doubly labeled water technique. Obviously, we talked about it earlier in the semester, but DLW was established in 1966 as a way of measuring the total energy and material balance of an animal using labeled hydrogen and oxygen isotopes. By 1987, the field metabolic rate of 46 mammalian species had been measured, including 23 placental or eutherian mammals and 13 marsupial or metatherian mammals. This is important to note because FMR data on those 46 mammalian species is summarized in a previous paper by the same author, and that data is used and updated in this paper. By 1994, when this paper was published, FMR of another 25 mammalian species had been measured. The purpose of this paper was more or less to update the findings of the 1987 paper using regression analysis and try to discern a trend that could be applied to all mammalian species. The author had established an equation for predicting field metabolic rates in his previous paper, and with more data, it obviously would become more accurate. The overarching question behind this paper is what accounts for variation in field metabolic rates between mammalian taxa. Nagy chose 4 possible criteria to explain the variation, the first being body mass, and that was shown in the previous paper to be a major determinant in variation. Habitat, diet, and taxonomy. Now, for taxonomy, the author focuses primarily on order, class, and infraclass classifications. So, why this question? Unfortunately for the field of bioenergetics, performing individual field metabolic rate measures for any given species is costly and requires specialized training. As a result, scientists don't have the resources available to measure the field metabolic rates of every mammal species. By creating a consistent model based on existing data, it is possible to predict a species FMR without having to actually go and measure it. This is especially helpful for wildlife managers, as it can help create a formula to predict food and energy requirements, and managers can base their management plans around those predictors. All right, so the data set that was used comes for the most part from previously established doubly labeled water measurements for 61 species. As all field metabolic rate measurements for the first 44 mammalian species studied are already available in the previous paper. It's easy to update and requires minimal additional research. The author used measurements for an additional 25 mammal species to update the allometric equations here and to search for a possible explanation for the variation between species. The mammals observed ranged in size from the 7-gram pipistrel bat to the 317-kilogram northern elephant seal. The data set included regression calculations, including data points on body mass, order, diet, habitat, and predicted FMR for each species. Body mass was measured in base log because it comes as allometric data, as we talked about in previous lectures. As this study consists entirely of analyzing previously established data, the methods section consists entirely of mathematical models. I'm not going to get into too much detail because there's a lot of detail to get into. The author used linear least square regression models to evaluate allometric relationships. A 95% confidence interval of regression line intercepts and slopes was used to determine significant variance between regression models. Analysis of covariance was used to compare regression lines between eutherians and marsupials. And an analysis of residual data was used to determine variation in field metabolic rates as the result of taxonomic grouping, diet, or habitat variables. The expected field metabolic rate of each species was based on body mass, was calculated for each variable and compared to actual results to determine significant variation from the norm. The analysis found that field metabolic rates in mammals ranged 1,600-fold from 29.3 kilojoules per day in pipistrelle bats, the smallest mammals, to 49,300 kilojoules per day in the largest mammals, the northern elephant seals. While the scaling was different for eutherian and marsupial mammals, it was found that most variation in metabolic respiration could be explained by differences in body mass. This conclusion lines up with previous estimations of mammalian scaling, but does not explain all the variability that was found. The author found no significant variation from the predicted field metabolic rate based on diet or habitat, suggesting that neither trait is responsible for variations in the regression line. Infraclass taxonomy accounted for approximately 1% of the variation not accounted for by body mass, but much of the variation is still a mystery. The addition of 21 new eutherian species significantly altered the regression line established in Nagy 1987, but the regression line for marsupials was not significantly different. This is not entirely surprising, as only 4 new marsupial species were added to this regression line. All right, so, Figure 1 here maps field metabolic rates and body mass in a logarithmic regression line. Predictably enough, larger mammals of both eutherian and marsupial species use more energy on a daily basis than their smaller counterparts. You can see here that the scaling of field metabolic rates differs between eutherian and metatherian mammals. The equation used to create eutherian and combined regression line varies significantly from the equation used in the 1987 paper, likely because of the addition of new data. However, as we said before, the marsupial regression line varies only slightly from the original line. Unfortunately, the data set for marsupials is still missing FMR values for major groups, such as carnivores and desert species. As a result, the marsupial regression line is not particularly accurate. Here, field metabolic rates are depicted as a percentage of the predicted field metabolic rate relative to body mass. The purpose of this figure is to show the amount of variation that isn't accounted for by body mass alone. There is obviously still a huge amount of variation unaccounted for, especially in eutherian mammals. Field metabolic rates for eutherian mammals can range anywhere from 34% to 204% of the predicted value, which is a range of 6-fold. The variation is slightly smaller for marsupials, but there is still a 2.5-fold variation that is unaccounted for by body mass alone. So what do these results all mean? Body mass is determined to be the most important predictor of FMR values along the scale. Together, taxonomic infraclass and body mass account for within 40% of variation in eutherian mammals and 21% in marsupials. However, other taxonomic values, such as class and order, as well as habitat and diet, are not considered reliable predictors of field metabolic rate. One exception of this rule is in desert eutherians, who can be expected to have an FMR 22% below the predicted value as a result of their habitat. That's the only instance in which habitat was a determining factor. The real takeaway is that no single factor accounts for a predictable fraction of the FMR variation not accounted for by either body mass or infraclass taxonomy. Despite the relatively large amounts of data used to reach these conclusions, the study was hindered by a relatively small sample size and an overabundance of certain taxa over others. For instance, there was a lot more data available for pinniped mammals, such as seals and walruses, when compared to shrews, whales, and large land megafauna. Including metabolic data on those taxa would likely result in a much different conclusion. In similar studies on birds, body mass was also found to be a major predictor of metabolic rate. However, there is still a good deal of unexplained variation in both mammals and birds, and more research is definitely needed to determine the cause. Other factors that might influence metabolic rate, but weren't included here, are daily weather patterns, sex, age, classes, time of year, and so on. An analysis of individuals in the same species could give way to more accurate predictors of metabolic rate. For instance, FMR varies wildly throughout the year, matching 92% of predicted metabolic rate in the... For instance, for springbok, FMR varies wildly throughout the year, matching 92% of predicted metabolic rate in the dry season, but a whopping 194% in the wet season. These factors could also conceivably... The factors mentioned earlier could conceivably amplify each other's effects on field metabolic rate, or potentially even cancel them out altogether. It is almost too difficult to predict the effects of a single variable on the overall system. So what's the legacy of this paper? According to Google Scholar, Nagy 1994 has been cited in 110 papers since its publication, including one paper published in 2019. Body mass is still used as an indicator of field metabolic rates in eutherian mammals, most notably in canids and other members of order Carnivora. As of 2005, doubly labeled water estimates of 229 terrestrial vertebrates have been measured, including 79 mammal species, 95 bird species, and 55 reptile species. The author, Ken Nagy, has since retired from studying field metabolic research and is now a herpetology and physiological ecology professor at UCLA. Thank you for listening to my presentation, and good luck on the follow-up.